Greetings from IIT Kanpur. So, previous lecture we discussed about thermal oxidation of silicon. We got started. First, we saw the properties of the amorphous SiO2 that is formed, some basic general properties, and then we discussed how oxide is grown and also a basic model, the Deal Grove model, and also some empirical models that are used for really thin oxides that may need to be grown. Now, the growth of the oxide, thermal oxide in silicon, has been the cornerstone in a way in the development of VLSI technology for MOSFETs, because the gate oxide silicon interface, the qualities, and also other oxides that are grown. So it's very important to know how much is how the oxide is growing, at what rate, and also what will be the final thickness of what we get. And often we may have some other thermal processes that may happen, and during that time also oxide thicknesses can change. So we need to be able to model all that and predict all that. So today what we would do is we'll dive a little deeper into that in the first part of the discussion, and then we'll also go into the gate oxide related issues that are very important for MOSFETs. So let's get started. So this is oxidation of silicon part 2. This is the disclaimer. So this is the overview which I had. This is the same slide which I showed in the previous lecture. So the first part we covered SiO2 properties and thermal oxidation of silicon. The second part we'll be looking a little bit details on the factors affecting oxidation of silicon, and then gate oxide charges in the MOS structure, which is the base of the MOSFET that is built, the transistor that is built. So let's get into the discussion on factors affecting silicon dioxide. For reference, I will give you the same textbooks that we have been talking about and referring to. So you can choose any one of them, and of course if you have access to more than, then you get a diverse view, but basic ideas are the same: SMZ, Gandhi, and Wolf and Tauber. So this is the outline of the first section of this lecture: the factors affecting SiO2, silicon dioxide, that is thermally grown. It turns out there are a variety of parameters that end up affecting the oxide growth, and that's true in nature. Often there are lots of indirect and direct effects, but here we want to be so precise how much is the oxide that is growing in our estimation of that value, that we would like to understand what are the parameters that can affect, so that reproducibly over wafer after wafer we are able to grow the correct value of the oxide. So it turns out, of course, the primary culprits for growing oxide, if I may say so, temperature and time. Okay, so how does this depend? We have already seen to some extent how it depends on time in the Deal Grove model. Then the ambient type that we have during the oxidation. It could be dry oxidation where only oxygen is coming mixed with nitrogen, or pure oxygen itself. Then we could have water vapor being brought by nitrogen, and you have the oxidation. Then you could have other environments also. You could have, for example, HCl. A little bit of HCl is introduced that brings in the chlorine, and so it turns out that the rate of oxidation really shoots up. We will primarily focus on the dry and the wet in this discussion. Substrate orientation, which we learned during when we talked about the substrate crystals. So it turns out 111 and 100, the popular substrates that are typically used, there is a difference in the way oxidation takes place, thermal oxidation takes place. And then ambient pressure, impurities that could be present, such as phosphorus and boron. They are dopants, but then they are in a way impurities in the crystalline structure, right? Then the wafer cleaning effect and the substrate doping effect. It may not be in this order, but roughly these are the points that we will be discussing. So let's get started. First of all, what will be the oxide thickness as a function of time for various temperatures? Temperature is the parameter, and it turns out that the two orientations are showing different values. What do we find? We find that the 111 is actually having a higher rate of oxidation. So you have higher thickness obtained in 111 silicon wafer compared to 100 silicon wafer. Okay, and as you go to higher temperatures, what do you find? The effect of the orientation stops having an stops playing a role. Okay, so that, because by then you will have thicker oxides. So when you have thicker oxides, diffusion is what is going to be primarily playing a role, at least initially. And then of course and at high temperatures, atoms are all moving so rapidly and randomly that the crystalline structures efficacy or the strictness of the positions are disturbed more when it is at high temperature, because they are all vibrating. So at that time you find that the reaction rates for 111 and 100 becomes the same. So this is a very good useful chart, and you can use such charts for finding out how much time you need to oxidize in oxygen or water vapor. Here of course it is wet oxidation, so we are using water vapor here, and you are able to predict what would happen. So let's look at it. So this is the Deal-Grove model schematic that we used. So here is the outside where you have the oxidizing species coming here. Then you have oxide that is already formed, and this is the silicon which is getting oxidized. So oxygen is diffusing through. This we already saw in the Deal-Grove model. Now it turns out, depending on which rate is limiting it, the amount of oxidizing species outside when you are doing the oxidation usually is high enough, and it's controlled by the solid solubility. So there is nothing much you need to worry about there. Depending on the partial pressure here, there will be a solid solubility, and based on that you will end up getting the diffusion that is happening. So from that it will go to the other end. So this is the diffusion limited step, and then at this end you will have F3 dominating, because this is the rate at which the silicon is consumed. So depending on which is the rate limiter, which is faster. If oxygen is coming very slowly, the atoms would have formed, silicon atoms would have formed SiO2, and they'll be waiting for the next oxygen to come. So but then if oxygen is coming at a very fast rate, especially when it is thin, that is the case, the rate limiting factor is what ends up being the limiting the whole process. So that is how you can understand why these variations are occurring. So let's go over it quickly. Time dependence, it is rate limited in the linear region. Why? In the linear region, oxides are thin, it's able to diffuse very fast, distance it has to diffuse very less, and you can see that the gradient will become shallower and shallower as the oxide becomes thick, right? So when it is close, the gradient is high, so diffusion is proportional to the gradient of the concentration, right? On the other hand, diffusion limited becomes sublinear, because when it becomes thick, the diffusion ends up slowing down, and then it becomes sublinear, and we saw that it becomes quadratic. We saw this in the Deal-Grove model already. Temperature dependence, although I showed some plots how B by A values, the linear constant and the parabolic constants, how they B and B by A, how they are varying. We did look at that. But typically the oxidation whole process with temperature has Arrhenius relationship. What is Arrhenius relationship? It is of the form a constant multiplied by exponent of minus delta E by kT. Okay, this is the classic Arrhenius relationship you will find in many processes. So that means there are two parameters that play a role: the prefactor and the barrier. So you may find that depending on the orientation of the wafer, the direction, the reaction rates will have different barriers that is to be overcome by the oxygen molecule and the silicon molecule to form the SiO2, right? So that delta E will end up playing a role in those cases. So, and on the other hand, the A will determine how fast it can, the reaction can take place, whether it's H2O or it is oxygen. So temperature, typically you have exponential dependence. So that means if I want to make a small change, it's actually either linear or quadratic. That's much slower. But if I change the temperature, so if I take more time, it changes slowly, right? On the other hand, if I end up changing the temperature, it jumps up exponentially, and you'll find that the rate goes up faster and faster. Now orientation will affect because of the orientation will be affected by the rate process, because the diffusion, once it is oxide, it doesn't matter to the first order whether the oxide is formed from from what orientation wafer, it's amorphous anyway. So the diffusion rate will be about the same, but the rate of reaction will depend on the number of bonds available. Depending on the facet of the wafer of the crystal that you have, the bonds that are available are going to play a role in interacting and forming the SiO2, right? So depending on the facet, the number of bonds available and the how the bonds are shared, all these play a role. So that's why the orientation plays a role in how fast something ends up reacting. And the activation also is anisotropic, because depending on the crystal, we find, if we saw, that is two face centered cubes which are offset about the diagonal, right? So that means depending on which direction you're approaching, you're going to have different barriers to be overcome in breaking the bonds, because neighboring bonds will also play a role. And also there is steric hindrance. Steric hindrance means when the reaction is taking place, if a new molecule wants to react with a neighboring atom, the reaction that is taking place may end up impeding the other one or coming in the way of the other one. So these factors will play a role, and which is why we find 111 and 100 there is a rate difference. And for a process person, what is more important to know and remember is 111 the rate of oxidation is faster, 100 the rate of oxidation is slower. Okay, this is the key point. The other point that you should remember as from the above is time is actually the rate of change of oxide growth is either linear in the initial stages or it will be sublinear. Okay, it won't just be a runaway process. Okay, on the other hand, temperature, if the temperature changes by 10 degrees, it's not going to be changing by the fraction of the temperature change, not the delta T versus by T. That fraction is going to be changing exponentially because it's in the exponent of this Arrhenius relationship, correct? So that's the key takeaway I want you to have from this slide. So I'll show a few slides which are available in many textbooks. And nowadays with Google and other web searches, search engines, you can easily get these things. It will be available to you. But what they do is normally in every fab, they come up with these charts, because they don't, the conditions in fabs, there may be some subtle differences which you may not be able to predict. First order, there should not be any difference, but you never know. Maybe it's a very humid place. So humidity, instead of being 40%, maybe 45%. How do you know? So for all the controls that we have, of course, they try to make sure it's absolutely controlled. But best is to work out in your lab, especially when you are working in your academic labs. It's best to check out what actually is happening in your processing fab. Okay, so here I am showing 111 wafers dry oxidation versus wet oxidation. Okay, and what do you see? Look at the scale. Even the scale here, the thickness is going from 0.01 to 1 micron, whereas wet oxidation I am showing here 0.01 to 10. Okay, I have taken this plot from Gandhi's book. Now what you find here is wet oxidation, you end up typically having a much faster rate of oxidation, and which is why you are finding that you are having to represent thicker oxides. You are not even coming above 1 here at 1200 degrees centigrade. On the other hand, 1200 and to 1200 degrees centigrade, you are coming to 2, 3, 4, 5 micron thickness. Okay, so clearly wet oxidation is much faster. That's one of the key takeaways you want. The other thing you notice is that typically the activation energies may be is likely to be lower for dry oxidation. So you'll find that you have to work this out. Okay, so first order, what you have to make sure is wet oxidation is faster than dry oxidation, and this is shown for 111. And to grow thick oxides, if I want to grow 5 micron, I would go for wet oxidation, because if I go by dry oxidation, it will take several tens of hours. You cannot wait that long. It's not good for your equipment to keep it at the high temperature, and also the energy that you are going to consume. On the other hand, you can achieve that at a faster rate with wet oxidation. So although there is no rigorous rule, but typically depending on the thickness, but if you want to go for very thick oxides, you go for wet oxidation. this is the plot that I'm showing for 100 wafer. Okay, and clearly the thicknesses are lower than that. So here you can see that again dry oxidation is slower, wet oxidation is fast, the scales are different, and since the rate of oxidation in dry oxidation is actually typically in the initial stages, because that's when the orientation plays a role. We saw that when you go to thicker oxides, it's diffusion that's going to play a role. So no longer will the orientation matter, and that is why you find that wet oxidation, at very high thicknesses, you're also reaching similar thicknesses, slightly lower maybe, but you're reaching 5 micron here also. So the key point I want to make here is 100 wafer being slower, and especially with dry oxidation, you can have a slower rate of growth. The same with wet oxidation also, you can go to a lower temperature, and today with controls it's possible, but as a default, if I want to choose something where to grow a thin oxide, I would go for dry oxidation, so that I can control the growth a little better. Something which is very fast, if there is 10% error, the error is actually much higher, right? So it grows a lot more, and error is on that is going to be more. So you want to be careful on that. So typically you want to grow slowly if you want to make a thinner oxide. Now that being said, it also turns out how you clean the wafer plays a role. Okay, why? Because the surface energy when you start off has an impact, and then eventually whatever impurities that may be there, that may be incorporated in the oxide, that could also play effect in the diffusion process of in your SiO2 that is formed. So there's good work done by this team, and this is often referred by many other people. So what you find is, if you have acidic cleaning, piranha cleaning, H2SO4, H2O2, you find that the oxide thicknesses you find for the same time of oxidation, this in dry oxygen 1000 degrees centigrade 100 wafer, the details are given. So you find the thickness is more compared to if you didn't clean the wafer at all, you just rinsed it and put it. And if on the other hand, if you put ammonium hydroxide H2O2, you find that it is lower. So what it means is, the way you clean plays a role, and you have to make sure that, because whatever is there ends up getting incorporated in the oxide also, right? So you have to be careful on that. And so key point, cleaning of the silicon wafer as per the procedure that you are following is imperative. It cannot be different at different times, and typically for gate oxides and critical oxides, you clean the wafer very thoroughly. Okay, and you after cleaning, you have to make sure you don't leave it there. Try to oxidize it immediately. So put it in the furnace immediately. In the laminar flow that we discussed last time, in the furnaces you load it and you start oxidizing it. Okay, so cleaning silicon wafer before oxide growth is a critical step. That's a point, takeaway message I want to give from this slide. So now, what is the effect of boron doping? Supposing I had a wafer which is p-type, and which is maybe doped with boron, another which is the n-type is doped with, say, phosphorus. So let us see what that does. It turns out, depending on the silicon's doping, your oxidation rates can be affected. So let us see here. What is shown is boron concentration is varying from 1 times 10 to the 16 to 2.5 times 10 to the 20. So what do you notice? If the boron concentration is higher, you find that your oxide thicknesses are higher. You find the top lines are all having the square symbol. The other one is a triangle or a circle, which are very close to each other. So, and what it also means is, for very high doping is when you see this effect a lot more. Lower doping, 1 times 10 to the 16 to 1 times 10 to the 20, difference is not as much as 2.5 times 10 to the 20. So very high doping means you are having some effect in the way the oxide is grown. Why is this happening? Boron gets segregated. This is an important point. It turns out there is we talked about segregation coefficient in terms of doping during the growth of silicon from a silicon melt, right? So similarly, any transformation from silicon to silicon dioxide, when it is formed, the impurities that are present or the dopants that are present in the silicon, they can get accommodated in the new material that is formed, or they can be rejected. So depending on that, there is a segregation coefficient again that is set up. So it turns out boron actually finds it favorable to move into the SiO2. So if you are growing oxide on silicon, say the initial doping was say Nd something, what you will find, sorry, Na, initial doping was say Na. As you grow oxide, at the interface you will find the doping concentration actually decreases. Why? The boron that is present close to the interface actually have preferentially gone into the oxide. Okay, so boron segregates into the oxide, leaving silicon, and due to boron segregation coefficient at SiSiO2 interface, this is a material property, and it turns out what happens when it goes into the oxide. When we discussed about oxide, we saw that it replaces the silicon position and interstitials will be created, and essentially what happens is it creates an environment where you will have a higher higher diffusion constant for the oxygen that is going through the oxide. So you end up affecting that. So what you find it increases the diffusion of oxidizing species through the oxide. So when you start off for very low thicknesses, this doping concentration may not play that much of a role because there is no oxide. It's limited by the reaction rate. But as the oxide becomes thicker, whether you are able to transport more oxygen or less oxygen will end up controlling the rate of oxide growth. So you find that because of the increased diffusion of oxidizing species, whether it's oxygen or H2O, through the oxide, due to the incorporation of the boron from the silicon substrate preferentially into the SiO2 during oxidation, your rate of oxidation increases. Now, when we talked about acceptors, we should talk about donors also, right? So let's see phosphorus Nd, what it would do. So this chart shows that at low temperatures there is a big difference between the doping concentrations. So here the square again is higher, but at higher temperatures there is no effect. Why could this be? So it turns out phosphorus has the opposite behavior as boron in terms of the segregation coefficient. As the oxide gets grown, whatever was originally in silicon remains in silicon. So it sort of piles up at the interface of the SiO2 Si interface. So the silicon becomes more heavily doped. Now what does that mean? So if it is heavily doped, when it is rate limited, that is the reaction is taking place at the surface, this plays a role. Why? Phosphorus ends up changing the Fermi level location, and as a result it makes it favorable for the oxidation to take place. Okay, it helps the ions move faster and all that, and ends up favoring the oxidation process. On the other hand, once the oxide has become thick, the rate is no longer limited, decided by the interface rate. It is decided by how well the oxygen is flowing, diffusing through the oxide. So once the oxide is thick enough, whether you are able to react fast or slow at the interface is not going to play any role because it's already limited by the diffusion. Okay, so this is an important point. So higher concentration of phosphorus actually shifts the Fermi level and increases the surface vacancy concentrations, and as a result it helps the oxidation process. So when reaction is diffusion limited, which is through diffusion oxide, you find there is no change. So for thick oxides, phosphorus doping will play no role. Doping concentration you don't have to worry about, but with thinner oxide you will have to. So when reaction limited, especially when it is thin and when you are starting off, the rate of reaction depends on the phosphorus that is present at the silicon interface close to the SiO2. Okay, so why are these nuances important? Because you want to model them. When you are making a device, you may have something which is lightly doped, heavier doped, something is phosphorus, something is boron, something is arsenic. You need to know how these things behave and how they affect the oxide growth rate, so that you are able to predict very precisely. And no wonder we are able to predict the thicknesses of oxides or to the order of 1 nanometer or so, right? So the reason is we are able to understand all these effects and we can account for it. So instead of if the rate is getting increased, we oxidize it for a shorter time or lower the temperature a little bit. So accordingly you will have to predict and do correctly what oxide you want to grow. And that's what is shown in the right side graph. If you see you find that the quadratic rate is constant, because it's that is if that has nothing to do with the reaction at the interface, whereas the linear rate ends up becoming high for higher doping concentration, because higher doping concentration facilitates the oxidation at the interface. So that was about doping. It turns out that ambient pressure also plays a role, and a lot of work has been done. Even my master's advisor, Professor K.N. Bhatt, had built a high pressure oxidation system. So what do we see here? This is the, for 111 and 100 wafer, this is the oxide thickness formation at 1 atmosphere. But supposing I can put it in a pressure cooker, you can increase the pressure, right? So you find that at 5 atmosphere and 10 atmosphere, 20 atmosphere, the rate of oxidation actually increases. Okay, and you find that the effect of the orientation does not matter, because the oxide is already thick, it is diffusion limited. Okay, so there is some good work by this company. If those interested can check it out. So this is another plot also from Gandhi's book, which shows what is happening. Of course, for very high temperatures, the pressure effect, it actually oxide growth rate, as we know, it becomes quadratic, and that's what we are seeing here. So what is the problem with this? It turns out that because it's a high pressure system and all, you have to worry about the equipment design. The size can be big, and throughput can be limited, because you have to pressurize the chamber and then depressurize before taking to the next step of the processing. And also the contaminations can be higher in this. So this is one reason that you end up not seeing too much of this high pressure oxidation system, although people do use it when they want to do the oxidation at a lower temperature but get a thicker oxide. Okay, so for constant oxidation, this is the rule of thumb that you may want to remember. For delta P of 1 atmosphere change, the delta T is changing by minus 30. It's as though you can get the same thickness with minus 30 degrees. Whatever is the original temperature, minus 30 degrees, you'll get the same thickness. So this is a good rule of thumb. For those interested can remember it. Pressure we saw, so clearly pressure could also be at the solid level. So there is a stress that can be there in the material. In fact, it does play a role. Okay, so it turns out higher the stress, slower the rate of oxidation. Okay, so that is less the curvature, less the T-ox that is formed. So corners in fact get affected, and it turns out that the concave surfaces oxidize faster. Convex surfaces, on the other hand, end up having less oxidation. So you have to watch out at the corners. You may get a thinner oxide at the corner. So you have to watch out on those. So an oxidation suppression at 800 degrees, lower temperatures get suppressed than at higher temperatures. Higher temperatures, what is happening? The stress probably is getting relieved because all the atoms moving so rapidly, and there's a little bit of fluidity in the oxide. Remember, oxide, we saw that amorphous SiO2 is actually like a glass. It's trying to flow, right? If you go to higher temperatures, it can flow a little bit more. So it probably takes away the stress. So this is an example of what could happen. Supposing you had a hole in silicon and you are trying to oxidize it, versus you will find that the concave things will oxidize faster. On the other hand, convex surface, if you had a pillar or these corners, you will find that the oxide is thinner. Okay, this is schematically shown here. Now in this pillar thing, I just want to say, so what it means is, as you keep growing, the oxide is going to keep eating into the silicon, right? So that means there comes a time when the pressure becomes high. Why? Remember that there is a expansion that is taking place when oxide is formed, and so as a result you'll have higher pressure. So so you'll end up finding that the pillars will be, finally the rate of oxidation will go so low, the pillar will oxidize at a very slow rate, or it's almost not oxidized anymore. So you can actually get self-limiting sizes pillar by these structures. So essentially the whole thing about stress is any reaction moves in the direction so as to remove the cause of the reaction, right? This is the Le Chatelier's principle you must have studied. That is probably the equivalent of the Newton's law, every action equal opposite reaction, right? So if you are trying to grow oxide, there is going to be some stress created, so the reaction will take so as to remove the stress, so it will actually end up slowing down. So that is the whole idea. Now people have tried out various ways to lower the temperature and time of oxidation, especially for thick oxides and so on. The reason is, if you have to oxidize for a long time, you are taking up the lab time, and that way the price of the wafer can go up. If you go to higher temperatures, again you are having to expend more energy to keep that temperature, and also the wear and tear becomes more when you go to very high temperatures. So always the effort has been to lower the temperature and time for oxidation. That's why you will notice we ended up using high pressure oxidation, then maybe looked at how if we can create stress. Of course stress sometimes is part of the structure of the wafer and the structures that you're building. So your effort has always been to lower the temperature, and if possible keep the time to within 10 minutes or so. If it is too small, again also can sometimes be tricky. Of course with automation you can work with it, but you want to have long enough so that you can control it, the process, to have very little variation. So it turns out there are two interesting approaches that are taken. One is with using plasma during oxidation and photons during oxidation. So plasma, it turns out, presence of oxygen plasma increases the rate of oxidation. It is not surprising, especially because plasmas are actually, cold plasmas have electrons at very high energy, right? So they may end up inducing these reactions. So whatever used to take place at a high temperature will end up doing at a slightly lower temperature in the presence of plasma. So it turns out that plasma increases. And the second thing is, because of the plasma potential that is created, the oxygen ions end up getting attracted. Okay, so that is one of the reasons you will find that this rate is going high. But then plasma is a charged environment, and some of these ions in the sheath will end up going sort of at an energy and get implanted, or at least hit the surface with some kinetic energy, so that may cause some damages. So usually plasma processes can have some damage. Of course you make sure you are able to know how much it is and remove it or minimize the damage, but you have to watch out on this aspect. Plasma can damage the oxide, because oxides may get charged up, they may end up breaking down. In fact, there's a lot of research that has been done on plasma processing, how much charging can occur, and how whether it breaks down the oxide or not. And then of course contamination is possible because of the metallic systems and all that. Then inferior electrical properties is seen with plasma grown oxide. So that's one reason it was never used for gate oxide or any other things. Okay, if at all you will use, if you just want to fill something with a lot of oxide and you don't mind the dielectric strength so much because it's very thick, so maybe in that, because very thick means the fields will be low, right? The two ends, if you apply a voltage, because it's thick, voltage divided by thickness will be the field. So you'll find that for such situations you don't mind maybe plasma grown oxide, right? So plasma is a mixed bag, but that opportunity exists. Similarly, photons. Can we stimulate the outermost electrons that are present in the materials that are reacting, and that way can the reaction be made faster? So it turns out it does play a role. So UV light exposure, ultraviolet, which is actually higher energy, so it takes the valence band electron to much higher energy. So that means that there are more opportunities open for the electrons going and forming bonds where originally there might have been a barrier, right? So the UV exposure, it does increase, especially for thin oxides. Okay, so that's what you find. Contribution of rate increases greater than the thermal effect. Whatever is the temperature for the same temperature, something more is happening. So it is facilitating the whole oxidation process. So these are some interesting tricks that people use. Okay. So let's see what are the takeaways on the factors affecting silicon oxidation. Oxide in VLSI being critical, we need to know very well how much is grown and what is the quality and so on. So that's why a lot of research has gone into this. And what I have shown is just some examples. There are people who try all sorts of ways to enhance the rate of oxidation or get a better quality oxide and so on. Okay. So you have to you can look up literature, and there's a lot of whole tons of literature in this subject. Thermal oxide in silicon is affected by a variety of factors, as we have already seen. Obviously, the main culprits, temperature and time. Then oxidation species, O2, H2O, and I have not discussed it here, but in chlorine environment, it ends up becoming faster. So that then orientation, doping, wafer cleaning, pressure, wafer contour, or what is present on the top, all those things end up playing a role. And you can also use some tricks of using plasma and photon to speed up your whole process. So as I said, one of the goals is to minimize time and temperature for oxidation process, right? Why do you want to minimize time? You want to save time that is spent in building the device. So if you can do it faster, it's always better, right? And then it's not necessarily true, but very often that's the situation. And temperature also, you want to keep it as low as possible. They call it the thermal budget. When you go to high temperatures, you're not only growing oxide, you're disturbing other dopings and making things move around. So you want to work with a as low a temperature as possible. And interestingly, over the decades, the operating temperatures, which used to be easily go to 1000 degrees, 1100 degrees and all, have lowered and come down to around 700, 800 degrees, typical temperatures of oxidation. Part of the reason is also you are requiring thinner oxides. However, oxides need to be of desired quality for application in VLSI. So you should make sure the oxide that you are growing by whichever method is good enough for what you want. Otherwise, it will be of not much use to you. Okay, so this is about the various factors that affect in the growth of oxide. Now we continue in this lecture and look at another very important aspect of this whole oxidation and oxide's role in silicon and all that. This is about the gate oxide charges. What are the charges that are present at the gate oxide of the MOS structure that you build? This is important especially because of the MOSFET, which is the backbone of the device that we typically device world for building circuits, correct? Now I have taken ideas here from Streetman and Banerjee, because it's a more of a devices discussion, but I'll bring in the processing aspects as we discuss how to minimize it, how to control it, and so on. Of course, Wolfentauber gives a good discussion also, very nice one, chapter 7 briefly. And then one of the classic books for MOS, those of you who are interested in device physics, this is a classic book, the traditionally one of the best book, Nicolaian and Bruce, and actually it's part of the Wiley Classic Library actually. You may even want to see whether you can get access to this book. It's a very good book for those who are looking into the device aspect about MOS. The whole book just discusses about MOS structure. Okay, so let's get started on this discussion. Outline. Initially, I will tell the types of charges that you are likely to encounter at the MOSFET gate. Then for each of those charges, I would like to just highlight what its origin is. Why does it arise? How does it affect the transistor parameter? And how do you control it, if possible eliminate it or bring it to negligible levels that it doesn't affect your device, to build reliable transistors. So first let's see what are the types of charges that are found in the gate oxide. So Si-SiO2 interface and oxide charges. So supposing this is the surface, outside world, you could have deposited something here, but typically when you start off, it's outside world. Oxygen is here during the oxidation. Then oxygen is coming in and going in, diffusing, and this is the silicon silicon dioxide interface. This is the scenario that you would find when you are oxidizing it. Now it turns out that interface is where the final interface will be the last oxidation that is taking place, correct? So this is where you'll have a transition region, because you have SiO2, these are all built earlier, this is just getting built, and then you have silicon. So around the time you terminate, how you terminate and all will play a role, and it turns out in the transition region, which may be SiOX, because some of the silicon is not completely oxidized, some of them are just starting to get oxidized, but the bond is broken but it's not oxidized. So you will find that transition region SiOX is a very thin layer at the SiO2 Si interface. It turns out now you have to do further analysis in material and also physics based analysis to know what it is. It turns out these are all fixed oxide charges which are positive charge. It turns out they are fixed oxide charge typically ends up becoming positive. Okay, this is an empirical fact, you can take it. So we represent it by the symbol QF, Q sub F. Then there are some other ions that come in. This is very fascinating. These are metal ions that can just move around in the oxide. So this is the mobile ion. Okay, and this is represented by symbol Qm. This mobile ion has its own signature. It plays its own role, writes its own story in the MOSFET behavior. Then comes something which is actually one of the most critical part of the all of them are important, but this is very critical because it's very, very nuanced. These are the interface states. You have is SiOX, right? But that is okay. But at the interface between Si and SiO2, Si is coming here, suddenly you find there is no Si, right? So there are lots of dangling bonds and all that. How are they tethered? Are they tethered at all? What is the role? These are known as interface states. Whether you like it or not, you will always get interface states. Okay, and this, if they are not passivated, they will end up giving rise to a charge. They could be positive, they could be negative. It could be a donor type interface states, it could be an acceptor type interface states. So depending on that, it may end up becoming positive or negative. So this is a very tricky thing, and these are actually can be represented as energy levels in the band gap of SiO2, not SiO2, Si. Band gap of Si, you can represent at the interface. These are levels that are present where they should not be present, right? Your conduction band, valence band, at the interface you will have some levels. So this is when if they are not passivated and they end up getting charged, you may end up getting, because that's what we are concerned about. In electronics, we are interested in what affects charge, right? So this can be represented as Q sub IT. IT is interface. And then that being said, all through the oxide, you could have some oxide trap charges. They can be positive, they can be negative, but typically they are positive, but you could have both. Okay, so there could be some place where we will have some impurity that is sitting and that is getting decorated by charges. So that is sitting in the SiO2. Of course, you don't want that. You want to make sure there are no impurities. That's why all this precaution is taken. Sometimes when you oxidize very rapidly also these things can happen. We'll see what is causing these. So this is the broad classification, and what is nice about it, it sort of captures what really happens, and it's reasonably predictable. Lots of research and work that is done seems to be built on this. It corroborates it, and it's also a lot more further understanding is built on this. So now it turns out as technology develops, all that we need to make sure that they are less than 10 to the 11, and after that we need not worry. So that is a 10 to the 11 per centimeter square on the surface, right? Of the order of 10 to the 14, 15 is where what is the surface number of atoms you will have. So almost 1 in a thousand these charges per unit area is what you can tolerate. Now why is this? I will request you to ponder over this. Part of the reason this is coming is because over time the gate oxide value is increasing. The oxide capacitance, Cox, is increasing, and the delta V that you see is inversely proportional to the oxide capacitance value. So when the capacitance is going up, even if there are charges there, you end up not seeing too much effect in the delta V. So as long as the charge for the current thicknesses of oxides less than 10 to the 11 and maybe even 10 to the power 10, it will not play a role. This is one of the few things which works in our favor, that as technology develops, this problem becomes less serious. It is important. If you don't do properly, it can go totally haywire. Okay, but if you do it carefully, usually it's not the thing that troubles you during the process. But and part of the reason is also because we have understood these things so well. So let's move forward and look at these charges one by one. So how does it affect the threshold voltage? Here we need to invoke a little bit of device physics, and I'll encourage you to review these ideas. So this is your MOS structure. The top can be metal. Nowadays many times you use poly, and again in modern devices again they have started using metal. So anyway, it can be metal, poly, something very conducting very well, oxide and silicon. Silicon is doped. It can be p-type, n-type, whatever. Here we typically take p-type as the background thing, because N MOSFETs is what we use as a typical standard, and P MOSFET is usually treated as an inverse of that. Okay. So now if you remember the relationship of the threshold voltage, Vt is equal to V flat band plus 2πb plus Q depletion by the depletion charge, that is by Cox. This is what you end up getting. Okay. Now one is actually the drop in the voltage across the oxide. Another you can say maybe VFB plus 2πb is from zero bias to the value of the threshold. What is the silicon drop in the silicon? What is the voltage drop in this region? Okay. Now the tricky part is this VFB. It turns out you will always have some VFB if there is a mismatch in the work function of the metal and the silicon. If you have identical, the work function of the metal is same as silicon, this is 0. But typically there will always be a mismatch. Okay, and you want to use the metal that you want plus something else. And this F something is a function of the charge that you find in the oxide. And this is what plays a role in changing your VT. The VT is one of the most critical parameters that you have in a MOSFET. And you need to be able to control it, predict it, use it. For circuit people will assume that that's what you're going to get. If it is not that value, the circuits won't work. So we cannot blame them after that. So you always, the goal is to put the ball in other person's court, right? So the processing people will have to absolutely make sure that their process parameters are on track, so that circuits people know and they can take it for granted, and then they can make sure the circuits are working properly. So this threshold voltage gets affected by the charges that are present. How does it get affected? We saw that F of it's a function of Qox. There are 4 categories that we divided: fixed oxide charge, mobile charge, trap charges, and interface charges that arise due to the interface states. Now this is how delta Vt will be affected because the contribution due to this, right? So it will be minus, assuming this charge is positive. If the charge is positive, it will be delta Vt will be minus for N MOSFET 1 over Cox, integrating all the way from this x equal to 0, x is from this direction, 0 to this point, 0 to xox, x divided by xox, rho of x is the charge density that is present anywhere, dx. This is a generic expression. This is essentially the first moment of the charge with respect to the location of the metal semiconductor place. Now it turns out, you can clearly see when x equal to 0, that is the charge is present at the metal oxide interface at the top, no problems, because its effect on the delta Vt will be nothing. Physically also we can understand, because this is directly connected to the metal, any delta V that will come and directly interact with this thing, and the fields will terminate there. If you put supposing there is a positive charge here, a negative charge comes here, so the positive charge fields will end up terminating on that itself. So there is no way it will be affected. So if the charge is at the metal SiO2 interface, its contribution to delta Vt is 0. On the other hand, if the charge is present at the SiO2 Si interface, the contribution is maximum. Okay, because xox divided by xo, if it is present at xox location, xox plus divided by xox is 1, you'll find that it has the maximum impact on this. And what will be its impact? The total charge Q divided by Cox. Okay, integration of rho, because all of them are sitting here, so it is just the total charge divided by Cox. So, as you can see, and which I mentioned in the when discussing the previous slide, as Cox becomes larger and larger, delta Vt becomes smaller and smaller. So if Cox is much larger, you won't have much of an issue with delta Vt, because there's hardly is going to be having a small impact. But of course, if the numerator Q becomes large, you are in trouble. So you have to make sure Q is below your the threshold of what is needed to keep delta Vt in the noise level. Okay, so this is the physics behind it. So let's dive into it and look at a little bit more physics as well as the processing aspects. So oxide fixed oxide charges, oxide fixed charges. So this is the surface SiO2, as we learned. It's located at the transition region where you have SiOX. How does it affect your Vt? They are all located right at the interface, so it will have full impact. The total QF divided by Cox. So usually the electronic charge is there, so you divide QF divided by Q will be given NF. So NF will be the density of fixed oxide charge per unit area that you have, and it is typically located within 35 angstroms, around 3.5 nanometers. Note that we are now coming to the boundaries of this, and anyway oxide thickness, oxide values are so high, this may not play that much of a role, but we have to be careful all the same. This is formed due to incomplete oxidation of silicon. And this turns out, and this is the important point that you want to note, for 111, these values are higher because there are more half oxidized levels that are left behind with 111 compared to 100. This is one of the reasons there was a transition towards 100 wafers for VLSI, because your fixed oxide charge was much less. Fixed oxide and other charges, but typically fixed oxide charges. In P substrates, it is more than in N substrates. Okay, this is mainly because of the way the oxidation terminates. As you can see, in P substrates, we know that boron will end up getting into the oxide. So that's one of the reasons you will find that the rate of diffusion will be more. So you will have more unfinished oxidation there. Okay, that's one of the reasons. And for wet oxidation is larger than dry oxidation because the rate of oxidation is higher in wet compared to dry, and that's where you have to that's one of the reasons why this happens. How can you minimize this QF? It turns out you can minimize this by, actually a lot of experiments are done, a lot of understanding was there, what could be done, what could not be done. If you do the process as per standard, one of the key things is whatever temperature you do, you terminate the oxidation process with nitrogen. So what happens is the temperature is the same, so whatever oxygen that is remaining ends up going and completing the oxidation as much as possible. So SiOX values, thickness of that becomes very, very small. So you are terminating in nitrogen so that you allow time for it to complete all the process. It's like an exam, you can suddenly come and say stop. So you'll find that some people has written half the answer, some would not. On the other hand, if you come and say, I'll give you 5 more minutes to finish, time is going to start. So, time is going to stop now. So that means it allows them to complete the whole process. Even if they may not try a new question, they may be able to complete what they are doing. The same thing here. So how do you detect this? And this is where again device physics comes in. There is a classic capacitance voltage measurement, CV measurement. I'll encourage all of you to read it up, because that's one of the ways in which you can detect all these oxide charges. The shift in CV, you have a ideal curve, and the shift that you get will tell you the delta VT, and this is one way of detecting it. Another way is, of course, if you built a MOSFET, you'll find your MOSFET values, threshold voltages are low. And one of the main reasons for that is there are fixed oxide charges. Then you may have to put something negative there to compensate for that. Now, to emphasize what I was telling about terminating the whole thing, Deal, the same person who was also involved in the Deal Grove model, he did some wonderful experiments, and this is the experiment, the classic experiment that you will find. So here the annealing temperature is very high. So what you need to do is, if you suddenly terminate oxidation at 1200 in oxygen, suddenly the temperature is dropping. As the temperature drops, you find that the fixed oxide charges go up. On the other hand, if you terminate with nitrogen, you 1200, stop the oxygen, start flowing the nitrogen, and as you bring down the temperature, you find the fixed oxide charges remains very low. Okay, so the whole idea is, whatever be your temperature of processing, instead of just terminating it, if for example you are 900, and if you just terminate it, it will end up going to immediately the unoxidized things will go here, and then it will go like that. Why is 1200 unoxidized is less? Because the temperature is high, so the rate of oxidation is whatever is there will quickly be able to finish the oxidation. So that's what you find. Now let's go to the other one. This is an interesting thing, mobile ion. And it turns out mobile ion often comes from humans who are there. Sodium is a prime culprit, because we have NaCl in our body. If you touch something, we may not realize it. Some NaCl from a sweat and other things will come in. So if you are not careful, you'll end up incorporating these in your oxide. So what do you find here? Depending on the bias you are applying, if I apply a positive bias on the top in the metal, what do I find? The positive will push the sodium and it will bring it here. If I apply a negative bias, what will happen? It will come towards the surface. And what did we see earlier, effect of the charge? When the charge is at the metal metal oxide interface, effect on the delta VT is 0. When it is at this end, SiO2 Si interface, maximum impact of the charge that is present. So this is precisely what happens. And it turns out the sodium ion can move around. When you apply a bias, even at room temperature, it moves around. So if you have an transistor and it's biased at some value, but you keep running it for some time, you'll find its threshold voltage slowly changes. So if you have an N MOSFET and you have put positive bias there, slowly you will find your threshold voltage decreases. Suddenly your leakage currents are going up, or the overall current is going up. So you don't know what is happening. It could be because of mobile charges. So it can be delta VT can be found out by this, and this is multiplied by I. I can be 0 when the charge is near the metal. I will be 0 when it's near the metal, and I equal to 1 when the charge is moved to this interface. So depending on the bias you are playing, there will be change. So it's actually remembers what bias you have applied. If you stop the bias somewhere, it can end up somewhere there in the middle as well. Okay. So mobile charges are positive and they are located within the oxide. They form due to ions getting into the oxide. Okay. And the ions are typically alkali metals, potassium, sodium. Heavier metals may be slower in diffusing, but they can also diffuse. How can you minimize QM? Oxidize in a halide environment. This is one reason I mentioned about HCl environment for oxidation. You often, when you are wanting to, you find that there is a lot of sodium contamination, whatever reason, you introduce a little bit of HCl during the oxidation, you'll find that it completely neutralizes the sodium that is there, because it's from NaCl, right? And then, but then the rate of oxidation changes, so you have to recalibrate your whole process. So O2 is often mixed with HCl or TCE or TCA, the essentially organic material. So that ends up sequestering the sodium. Gettering with phosphosilicate glass. So if you have phosphosilicate glass and take it to high temperature, the sodium, once it comes to there, it will get trapped. It will not be able to move. Another thing you can do is, you can, if you have a wafer and over time you don't want sodium to somehow get in, you cap it with nitride layer. Silicon nitride, this is one of the advantages, very good sealing agent. So if you do that, once the device has been processed, chance of sodium and all coming in becomes very low. How do you detect it? Again, CV measurements. You find shifts in the CV curve, and also if you have transistors, you will find that it is flipping from one state to another. It could do that because the threshold voltage is changing, so it will end up affecting your circuit. There is a history. So once you apply a positive bias, you get some response. You keep then you go back and apply a lot of negative bias, and then come back and measure, you will get something else. Now let's look at the next thing. Then this actually is the trickiest, as I mentioned, oxide interface charges, or QIT. Actually, I was reminded when I was putting together this slide of this statement by Wolfgang Pauli. God made the bulk. Surfaces were invented by the devil. The reason is the bulk is easier to control and understand and predict. It's much more predictable. The interfaces is where most of the challenge comes, and this is where one has to be very careful. And one of the most important places, interfaces where it is important, is the gate insulator silicon interface. That has to be very nice, because your crystalline material coming, terminating, and all the bonds should be nicely tied down, tethered down. So I am representing this by some symbol here. Essentially, these are states in the band gap, and I will encourage those of you who are more interested to read up. This is very fascinating and wonderful math and wonderful physics and wonderful way to model reality, what is really happening in nature. So QIT, depending on what this is, not, you cannot say whether it's positive or negative, depends on the way in which interface states are formed. So as you are going sweeping the whole thing, you will find that the Fermi level will go through the band gap. So whether you end up getting positive charge or negative charge during the threshold voltage switch, you will have some total charge QIT, which is essentially Q times DIT. DIT is the interface states per electron volt in the energy gap. So integrate over the whole band gap. The total DIT, if it is positive and negative, they should cancel off. So, but if it's all positive, it will add up, all negative will add up in the other way. So this and that will end up giving you QIT. This is possibly because of passivation, non-passivation of dangling bonds. There are lots of theories. We have a pretty good understanding, but cannot say we fully understand. There are always things that are beyond us. So, higher for 111 again, and lower for 100. As I mentioned, this is one of the reasons. Fixed oxide charge is also better for this. So, and high temperature oxidation is actually better for interface states, because these dangling bonds can be better tethered. You can minimize DIT by doing some of the following. In fact, I myself had to use this one time when I was making devices, and really suddenly all my devices started working well, because I was able to passivate the dangling bonds. Post metallization, after the metal, and those days aluminum was used, especially the one device I made had aluminum on top of it with nitride capping. Now what happens is aluminum will react with the moisture or something a little bit, and then it may release hydrogen, and that ends up passivating the dangling bonds that may be present. Another thing that people do is they anneal at 350 to 500 degrees for about half an hour in forming gas. Forming gas is essentially hydrogen, 5% hydrogen, 95% nitrogen. Hydrogen is flammable, so you want to mix nitrogen to make it, prevent it, to keep it safe. Or sometimes you may anneal the whole thing in argon also. So then that ends up passivating the bonds. Essentially, you are taking it to high temperature, and often they end up finding a more stable state, and they may get passivated. Hydrogen, in fact, reacts with aluminum. That this is one thing. So this is one of the process that you can do. The other process is high temperature post oxidation annealing in H2 or inert nitrogen argon. So you can just take it to high temperature, anneal it, maybe 350, 500 degrees centigrade. You don't want to take it too high a temperature also. So and then you end up finding that it gets passivated. The H2O that may be present in the dissolved in the wafer or something, those things might be helping in all this. So how do you detect this? CV measurement again. What you find is the CV stretches. That is the thing. And one of the most tricky part here is it can take any form. Only after you measure it, you know what it is, or if you know what defects are going to come, then maybe you can predict. And usually the thing that is affected most, besides the, even if threshold voltage is not affected, say 50% of the charges that are present is positive, 50% negative, maybe Vt will be, delta Vt will then be 0, because overall charge becomes 0, right? But the problem with this is it will end up stretching the CV. That means you take much more voltage in order to switch the transistor. Okay, so you'll find that you'll end up having problems. So subthreshold swing measurement is important. Deep layer transient spectroscopy is one of the ways to measure it. This deep layer transient spectroscopy essentially looks at the levels that are present in the forbidden region. Finally, oxide trap charges. These are charges that may be present in the oxide itself. This is essentially Q times Nt, that is the total charge that is present, but the way it affects is different, because depending on where the charge is present, its effect on delta Vt will be different. So you end up having this, the original equation that we used for trap charges. This is most pertinent, and this is how it should be: 1 minus 1 over Cox integrated from 0 to Xox rho of t x dx. This can be formed by, why does this form? Supposing during the oxidation there was a sudden change in temperature or sudden drop in temperature. So some oxides were not formed properly. So as you are oxidizing, the interface, actually the interface supposing was somewhere here, it slowly moves there, right? So supposing somewhere in between, if the oxidation didn't take place, that interface you'll find some improperly oxidized and broken bonds, and that could end up trapping charges. Hot electrons and hot holes during the processing, during the working of the device, you can have energized electrons and holes will end up getting trapped in the oxide, and that's a big challenge actually. And of course, radiation environment. If you go to space, these problems are common. So you'll have to make sure you are able to address it. How do you minimize it? Once the process is done, again similar to what we did in the earlier case for DIT, post metallization anneal with nitride capping in the forming gas, which we did, which was very similar to the other one. This also helps for oxide trap charges. Another thing you can do is you can take it to very high temperatures and do annealing in H2 and inert gas. Again, the same thing as what we did for DIT. Essentially, what you need to do is those traps that are present, you want to satiate them with something which is more benign, which doesn't cause any charge there. How do you detect it? Again, there is a threshold voltage shift, and depending on what it is, it will be positive or negative shift. So threshold, then the other thing is subthreshold voltage change also you can find out. You can find out how it is changing. So now CV that I've been talking about, this sort of captures all the different charges. If we have a diagram, so you'll find that this is the ideal. Now if there is a fixed oxide charge or some positive charge that is present at the interface, it will shift this way. If it were this alkali ion, when you have negative bias, you are actually pulled it to the metal surface, right? So it will be like this. And then when you, because it is positive, you have pushed the ion towards the interface, it will come back like this. So if you do a sweep, you'll find this hysteresis. That's one of the ways to know that there was a mobile ion. For DIT, of course, it can take any shape. I've shown something arbitrarily. As you can see, it has stretched from here to here. Okay, it completely stretches the thing. And one of the MOSFET subthreshold swing, which is a very critical parameter, probably the most important parameter today, in order to switch on and off the transistors. This is one reason we want to go to tunnel FET and all that. So if you look at the expression for that, this is KT over Q natural log of 10, 1 plus C depletion plus CIT divided by Cox. If the this is something C depletion and Cox you cannot get away from, that exists, right? But CIT is something you can get rid of. So you have to get rid of the CIT interface states, and that ends up affecting your subthreshold swing, and this is something critical for your MOSFET's behavior. So how do you control it? Just a recap of these because it's useful to know. QF, fixed oxide charge, terminate oxidation in nitrogen or argon. just terminate in that. It's little, you're annealing at 1200 degrees, oxidizing at 1200 degrees centigrade, turn off the oxygen, start the nitrogen, and then slowly bring the temperature down. Mobile charges, remove alkali and other mobile metal ions as much as possible by cleaning the furnace with HCl before you start. You can do that. HCl will, the Cl ion in that will end up reacting with these metals and sequester them. You can, when you wash, they dissolve and go away. Oxidation in chlorine environment ensures that these ions will not play havoc. Gettering with phosphosilicate gas, nitrogen capping. These are the processing methods of controlling these charges. QIT, use pure gases so that there is a steady oxidation and you are not getting something else happening. Forming gas anneal post oxidation is a wonderful method of doing it. Forming gases H2 and nitrogen, and or you can use argon at high temperatures of not exactly high but intermediate temperatures, 350 to 500 degrees for about 30 minutes. That's actually a good way to complete your MOSFET process in the traditional method, older methods. You finish the making the device, just do an anneal. Then trap. One of the things that you can do to avoid it is avoid hot carriers. Hot carriers were a big problem, especially when for short channel effects, especially when voltages were very high. Today, luckily, the voltage of operation for some of the more advanced devices is very low, below 1 volt. So that being the case, the hot electron effect for SiO2 system actually is not so common, but still you should be careful about this. And of course, radiation environment, you avoid those. And once if it is found, you can again do some annealing to at least temporarily passivate those. Why I say temporarily is many times when you passivate with hydrogen or something, if again a high temperature is seen, the hydrogen may escape. Then you'll again be left with that same problem. So this is the takeaway of gate oxide charges, a very important part, especially for the SiSiO2 system, which is the backbone or the keystone or the core part of MOS technology. At least till now, today we are using other oxide, but still you end up using SiO2, maybe a very thin monolayer or something. So thermally grown SiO2 and Si is the keystone of a MOSFET technology. Okay, and charges can be present. You want to avoid that, otherwise it will end up messing with your threshold voltage, affecting a subthreshold swing. Subthreshold swing is very unforgiving. If you do that, your transistor will be leaky, or you may not get the high enough drive current, whichever side we are shifting it, because it's getting stretched, no? The on and off, the voltage that you have to apply to turn it on and off. So charges can be fixed oxide charge, mobile charge arising from interface states, or oxide trap charges. You need to know the effect of each types of on the MOSFET behavior, and those who are planning to work on semiconductor processing in the VLSI field, I would encourage you to know this subject quite well. Even others who may be doing work in other technologies, the way the science has technology has developed and the way it is explained actually gives you a lot of insight into the physics of how these devices work. So it's worth knowing. Need to know why these charges get formed in the gate oxide. If you know them, you can prevent it in the first place. There are ways to mitigate their formation right at the start, and what if they are there are ways to at least mitigate it, if not eliminate it. Gate oxide growth is one of the most critical steps MOSFETs in the VLSI, and it continues to be, although we are using a lot of other things, continues to be. And it is not just in the VLSI world, even for many MEMS applications and many other types of applications where you use silicon dioxide system, being so well studied, really comes in handy. It's very predictable and it's very useful for a lot of applications. So with that, we'll conclude this discussion on thermal oxidation of silicon, and we'll move on to the other unit processes. See you in the next lecture.